Okay. The next part we have to prove that the maximal elements in M are prime ideals. So, let P be a maximal element in this M with respect to the inclusion. To prove P is a prime ideal, we need to prove that given A B in the ring A with A times B is in P, we want to prove A is in P or B is in P. This is what we need to prove. So, I will assume that both elements are not in P and look for a contradiction, and contradiction to what we should guess for that P is the maximal element in M. So, let me go to the next page. So, let assume that both A and B, they do not belong to P, and consider P ideal generated by P and this A, that is this, and P and ideal generated by B. So, both these ideals strictly contain P, that is because A is not here, B is not here, but A is here, A is not here, B is here, B is not here. So, this is a strict containment. Therefore, P plus this ideal cannot be in M, because if it is in M, that will contradict the maximality of P. Similarly, ideal generated by P and B, this cannot be in the set M, because P is maximal. Since P is maximal in M. Alright, what does that mean? That means it already contains P. So, therefore, the only thing which could go wrong is P intersection P plus A, this intersection S is non-empty. Similarly, P plus AB intersection S is also non-empty. But that means what? I choose an element S here, which is in S, and this ideal. So, that means S is of the form P prime plus CA, and I choose similarly an element S prime, not P prime, P, where P belongs to P and C belongs to the ring A, and here I choose S prime in S, this is in S, S prime is in S, which is also of the form P prime plus C prime B, where P prime is in P and C prime is in A. Now, when I multiply S and S prime, this is in S because S is multiplicatively close. On the other hand, I will multiply it out, then I will get P prime plus C prime B times P plus P prime CA plus C prime AB. But it is clear that this is also in the ideal P, because P prime is in ideal P, P is in ideal P, P prime is in ideal P, and AB is also in ideal P by assumption. So, here since AB is in P, but then this is in S, so this contradicts contradicts the assumption that P intersection S is empty. So, therefore, this completes the proof that the maximal elements in this M are prime ideals. Now, let us continue. So, I still want to write some more applications of this theorem now. So, let me deduce some consequences from this theorem. So, let us write it as a corollary 1. All right. So, let us start with a non-zero ring. Let A not 0 be a ring, and A is a ideal which is not a unit ideal. Then A is contained in M for some M belonging to the maximal ideals. In particular, SPMA is non-empty. This is again we have proved this is Krull's theorem. Proof. Earlier we have proved it as a application of Zorn's lemma. Of course, here in the theorem also we have used Zorn's lemma, but we proved that theorem as a consequence of the localization. So, similarly, this corollary will be consequence of the earlier theorem. So, apply earlier theorem by taking S equal to singleton 1. Then because A is not equal to the unit ideal, this A and S they do not intersect, and therefore I can apply a theorem, and then we can say that there exists a maximal ideal actually. All right. So, next consequence, corollary 2. Remember, if you take S equal to 1, then what is S inverse A? S inverse A is just given ring A. So, therefore, by the next part in the earlier theorem, those prime ideals are actually maximal ideals. All right. So, corollary 2, let A be a ring, then this describes the units, complement of the units A minus A cross. This is precisely the union of M, where M varies in the maximal ideals of A. Proof. Well, if you have this containment first, this containment. So, let us take U in unit. That means there exists U prime in U prime in A with U prime U equal to 1. So, so I have taken element which is not here, because I have omitted here A units, I have started with here. So, I should prove that it does not belong to any of the maximal ideal. So, if U belongs to some maximal ideal, then U prime will also belong to M, but 1, that is 1. So, contradiction. Maximal ideals are proper ideals. So, that proves this inclusion. So, this inclusion, if I take element in a maximal ideal in the union, then similarly I will take a complement U belonging to A minus union in the M in the maximal ideals. I should show you this is a unit, but this means U cannot be in any maximal ideal. So that means ideal AU, ideal generated by U, cannot be in any maximal ideal for every M. But by earlier corollary, by corollary 1, AU must be the unit ideal. So because if it were a proper ideal, then it is contained in some maximal ideal. So that is U prime equal to 1 for some U prime in U. So that means U is a unit in A. So we have checked the complement of this right hand side is contained in the complement of this, which is units. So therefore we have proved this inclusion. This was already proved. So that proves corollary 2. Alright. Now, okay, next corollary 3. This I want to prove again that nil radical of A equal to intersection of P belonging to spec of A. So proof. Alright. So first of all this inclusion. So if you take an element A in the nil A, that is A is nilpotent, A power n is 0. For some n in n, there exists n in n such that A power n is 0, but 0 belongs to P for every P, but P is a prime ideal, therefore by induction you prove that A belongs to P, and therefore A belongs to RHS for every P, therefore A belongs to RHS. Now the other inclusion, I have to prove that an element A which is in every prime ideal, I want to prove that it is nilpotent. So start with let A belonging to the intersection P belonging to spec A, to show that A is nilpotent. Suppose not. Suppose A is not nilpotent, that is A power n is never 0, then we should get a contradiction. Alright, now you consider the set S, which is a multiplicative set generated by A, that means you take all powers of A and none of the power is 0. So that means S don't intersect with the ideal 0. So by theorem, there exists a prime ideal P such that P intersection S is empty, but then no power of A power n will not belong to P for every n. In particular, A will not belong to P, but on the other hand we started with A belong to the intersection P, so therefore this is a contradiction. So this proves the corollary. Alright, now one more. So this is very important for as far as the geometry is concerned. So this is corollary, next corollary. So, which is this? Corollary 3, corollary 4 it is. Corollary 4. Let A be an ideal in the ring A with A is a proper ideal, A is not equal to the whole ring, then radical of the ideal A is precisely the interest. So, radical of the ideal A, what was the definition? Let us recall, this is all those A in A such that some power of A belongs to the ideal A for some m in n, but as you see it is difficult to check what is this ideal. So, this is same thing as this is the assertion, intersection of all those P where P varies in the spectrum of A with A is contained in P. All the prime ideals which contain P, if you take their intersection, then you get the radical of A. So, proof. Proof I will recall the following observation which we have already done earlier. So, given the ideal A, we have this residue class map. This is the canonical surjective ring homomorphism. And what do we know about this, the ideal structure? So, we know that the ideals of A by A and some ideals among the ideals in A. So, that is all those ideals B in ideal of A which contain A, where A is contained in B. This set, this is not all set of ideals, this is contained in that, it is only I am taking the subset, and we have a bijective correspondence between them, these two sets, namely this B goes to B by A and inverse is obviously the contraction map. So, this is a bijection. Not only this, moreover, if I consider the prime ideals, so spec of A which contains all those prime ideals P in spec A such that A is contained in P, this subset is precisely the spectrum of A by A. This is a bijection. Under this bijection, prime ideals will go to prime ideals of the residue class ring. This is a bijection, and these bijections are also inclusion preserving. Anyway, so we know the structure. So, if you look at this residue class map ring homomorphism A by A. Now, in this let us look at the nil radical of A, nil radical of not of A but A by A. This is by definition, it is the intersection of all prime ideals in this residue class ring, but they are of the form P by A, where P is a prime ideal in A and P should be containing A. But when I try to pull back this, so when I if you call this map as pi, then if I take pi inverse of the nil radical of A by A, this is a contraction. What is this contraction? Then each one of them I have to contract and intersect. So, and what do I get? First of all, note that this is precisely the radical of A on one hand, because if somebody goes to the nil radical, so this is I am explaining this is because if A belongs here, A belongs to this, that means pi of A goes, so that means pi of A is nilpotent in A by A, but that is pi A power n is 0, but pi A power n, because pi is a ring homomorphism, this is pi of A power n, that is 0. Therefore, A power n belongs to the kernel of pi, and this kernel of pi is contained in pi inverse of nil radical of A by A. So, therefore, A belongs to the radical of A. This A belongs to the radical of A. On the other hand, when I intersect each one of them, the contraction commutes with the intersection, and when I contract each one of them, I get P. So, therefore, on the other hand, this is intersection of P, where P should be a prime ideal and P should contain A. So, we have proved this equality. So, this equality is proved. That was precisely the assertion. So, that proves this corollary. Now, now I want to prove the existence of minimal elements. So, this is a very short theorem. So, let us prove it and then we will end the lecture here. So, theorem. So, let A be non-zero ring, A equal to non-zero ring, then the ordered set spec A with inclusion has minimal elements. So, in fact, we will prove that every prime ideal P contains a minimal element in spec A. Proof. Consider, so start with the prime ideal. So, let P be given, and we know such a P exists by earlier discussion, and consider M, which is all those prime ideals Q such that Q is contained in P. This is a subset of prime ideals and it definitely contains P. Therefore, this is non-empty. Now, I want to check that this has every chain. So, let us start with the chain, because if I want to conclude it has minimal elements, I want to apply Zorn's lemma, but I will apply Zorn's lemma not to the M with usual inclusion, but I will apply it to the opposite set. So, I will prove that every chain has lower bound. So, let C contained in M be a chain and consider this intersection Q belong to C. We shall check that Q we shall check that this intersection Q in C is a lower bound for a C in M. So, that means I have to check that first of all this element is in M and it is lower than every element in C. So, it is clearly This is clearly a lower bound, that is clear. This is clear. Because it is intersection, it is contained in every Q in C, therefore it is a lower bound with respect to this inclusion. And now to prove it is in M, I have to check it is a prime ideal. But note that to check that intersection Q in C is a prime ideal, we will check that the complement is multiplicatively checked. A minus intersection Q in C is multiplicatively close. In A. But what is the complement? But this complement, but A minus intersection Q in C, this is nothing but this will become union and A minus Q where is in C, and each one of them is multiplicatively close. And it is a chain, therefore there is a containment relation between them. So therefore this is multiplicatively close. That implies it is multiplicatively close. Because if I have, first of all, one belong there, secondly if I have two elements here, it will belong to two elements, let us say, but I will choose one of the Q, both the Q and suppose it is Q prime, they are comparable, therefore this complement will have containment relation among them, therefore I will work in a bigger set which is multiplicatively close, therefore the product will be there. So this implication is very easy to check. So we have checked, so that means we have checked that C has a lower bound in M, therefore if I take now the ordered set, this opposite ordered set, this is nothing but the set is same, but the order is opposite. This means it is this. So inclusions will get reverse. That means this set, any chain in this set, that minimal will become maximal. So therefore I can apply John's lemma to set. So therefore we can apply John's lemma to the ordered set M, this, to conclude that M has maximal elements with respect to this, which is opposite of the natural inclusion, and hence M this has minimal elements. That was the assertion. All right. Now as a result, one can easily prove corollary. The zero divisors of the ring A equal to union P, where P belongs to M, which is a subset of. In fact, we can take this M to be the, so we can take M precisely to be all those prime ideals P such that M intersection P intersection S is empty, where this S is, so S is non-zero divisors in A, the set of all non-zero divisors, which is multiplicatively closed set, and now apply the earlier result and you will get this equality. Right now we do not know this M is a finite set or not. Okay, right now we do not know whether M is a finite set or not, but we will prove that if A is Noetherian, then this M is actually a finite set, and this I will just simply write here, check this equality by using earlier theorem. Okay, what earlier theorem says that this set has precisely the property that all the guys are in a zero divisors. So check this formally. So with this I will stop for today, and we will continue in the next lecture localization of modules, which is also very important topic, and after that we will then start geometry again, the geometry of the maximal spectrum of the ring and the prime spectrum of the ring. Thank you very much.